Physical Sciences, grade 12 paper for Johannesburg North District, March 2024. So it's the one that we want to revise here. I will skip the instructions for the sake of time and progress. So it's consisting of two sections, section A and section B there. So I'll just quickly go straight to the first section A. Right, multiple choice questions first. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write down only the letter A to D next to the question number 1.1 to 1.3 in the answer book. Right. 1.1 was saying 2 isolated bodies A and B having masses m and 2m respectively are placed a distance r apart. Consider the following statements regarding the gravitational force exerted by the bodies on each other. Right. Item 1 is saying the force exerted by B on body A is half that exerted by A on body B. That's not correct. Actually, they exert a force of equal magnitude to each other, of course, opposite direction. So item 2, they saying the force exerted on the bodies is independent of the masses of the bodies. That's not true. Actually, it's dependent. Item 3 is saying the force is exerted on body A by the force exerted on body A by body B is equal but opposite to that of body A. This is correct, right? And then the forces will always be attractive. That's very true according to the law of universal gravitation. They are always attractive, right? So the correct answer therefore is item 3 and item 4 only, which is C. That becomes our answer. So for 1.1, it's C, right? 1.2, an object is dropped from rest and after falling a distance x, its momentum of the object after it has fallen a distance to x is still p, apparently product of mass and velocity. So it is dependent to the mass and velocity only, right? So it will still remain the same. Let's go to the next question. So the next question, 1.3, saying the graph below shows how the momentum p of an object changes with time t, during which one of the following time intervals measured in seconds is the magnitude of the net force acting on the object the greatest, right? So we are checking where can we have the greatest change in momentum, because net force apparently it is the rate of change of momentum. So where are we having the change in momentum? Which time interval are we going to have the rate of change of momentum being the greatest? Apparently, it will be between 3 and 4. It is whereby if we subtract 20 minus 10, that's where we can get the greatest change in momentum, which becomes 30 kg meters per second. We can't get that any other change in momentum that can be greater than that. So it therefore means that 1.3 is what? D. That's our answer there. That's the time interval that will give us the greatest change in momentum, so that we can also have the greatest magnitude of the net force, right? Because a net force is directly proportional to the change in momentum, right? Let's go on to question number 2, right? Question 2, it's saying a block of mass 8 kg is placed on a rough horizontal surface. The 8 kg block, which is connected to the 2 kg block by means of a light inextensible string passing over a light frictionless pulley, starts sliding from point A as shown below, right? State Newton's law in words. So it states that when a resultant force acts on an object, the object will accelerate in the direction of the force. An acceleration directly proportional to the force and inversely proportional to the mass of the object, right? That's 2.1 there. 2.2 is now saying draw a labeled free body diagram for the 8 kg block. So I just want to quickly just draw it here to indicate how it's going to be, right? So number 1, the object itself shall be represented by a dot. So I will indicate my dot here, right? Then there is a normal force acting upwards. I will draw the normal force there. I'll label it as N. Then we have the gravitational force acting downwards. There is our gravitational force. It's acting downwards. We can say Fg, we can say W for weight, will still be correct. Right, then we have a frictional force Fk acting in this direction. There is our kinetic frictional force, so we label it as Fk. Right, and then we have our tension acting at an angle. There it is. So we can indicate it as well as our T there. Right. Apparently, that's our diagram there. Right. I just want to indicate it nicely. Right. So there we go. Right. That's T there. So that becomes our free body diagram. We can be guided by the marks that we are seeing there, which means we have to come out with 4 forces. Right, we've answered that 2.2. Let's go to 2.3. 2.3 is saying when the 8 kg block reaches point B, the angle between the string and the horizontal is 15 degrees and the acceleration of the system is 1.3 meters per square second. Give a reason why the system is not in equilibrium. It is because there is an acceleration there. We see that the acceleration is 1.32 meters per square second. So because we have an acceleration, the system is not in equilibrium. So we can simply say there is an acceleration, or we can say the acceleration is changing, or it's changed. So that's 2.3.1. 2.3.2 is saying use the 2 kg block to calculate the tension in the string, right? So what can we do? First things first, we can use Newton's second law. So by saying F net is equal to ma for the 2 kg block, taking downward forces as possible is a choice that we can take. F net is equal to ma. Right, so which are the forces that are acting on the 2 kg block? Apparently, there is gravitational force that is acting downwards. Then there is also tension that is acting upwards. Right, so we have the tension that is acting upwards there. Right, so we can simply say Fg, the gravitational force, minus T, the tension, is equivalent to ma. Right, so substituting what we have, 2 multiplied by 9.8, since gravitational force is equivalent to mg, right, minus T, the tension, is equal to 2 multiplied by 1.32. We have taken downwards as what? As positive. So we can make T the subject. 2 times 9.8, that's giving us 19.6. Minus T is equal to 2.64. Hence, we can transpose them. 19.6 minus 2.64 is equal to T. Right? So therefore, T is equal to 16.96 Newton. This becomes our tension. We have arrived. Right? So that's our tension. There we have answered that question. Let's go to the next question, which is now saying, calculate 2.3.3, calculate the kinetic frictional force between the 8 kg block and the horizontal surface. So now we have the tension. So we can still say for the 8 kg block, we can still do the same thing again to say, okay, F net, according to Newton's second law, F net is equal to ma, right? So just out of interest, I might want to mention that oftentimes when the examiner gives you, for example, like 2.1 is saying the state Newton's second law, that can also serve as a hint to answering the questions that are following. You can also try to think along those lines of what the examiner was asking you to define or to state at the starting point there. You can also think along those lines. That's why you see now we are using the Newton's second law of motion to answer the questions now. F net is equal to ma. Right. So which forces are we referring to? We are talking of the 8 kg block. So let's go to the 8 kg block. Right. Apparently, we have Tx here, the horizontal component of tension. It's acting in this direction. Then we have our Fk, the kinetic frictional force that is acting in this direction. This is the horizontal dimension where the acceleration is taking place. Right, so we can therefore say Tx, the horizontal component, minus Fk, the kinetic frictional force, is equal to Ma. Right, so we have calculated tension, we got 16.96. So we are going to say Tx is now given by T cos theta. So it means 16.96 cos 15. That's our Tx. Minus Fk that we are looking for is equal to M, the mass of the 8 kg block. That's 8 multiplied by 1.32. And that can give us, okay, we can just simplify at this side to say 16.96 cos 15 minus, okay, 8 times 1.32, apparently we get 10.56 is equal to Fk, right? Then we just punch this on the calculator. It's going to give us 5.822108. So it means Fk, therefore, is equal to 5.82 Newton. That becomes our kinetic frictional force. Okay, we've answered 2.3.3. Let's go to 2.4. 2.4 is saying as the 8 kg block moves from B to C, the kinetic frictional force between the 8 kg block and the horizontal surface is not constant. Give a reason for this statement. So they are saying as the 8 kg block is now moving from point B, which is here, to point C, which is here, the examiner is asking the kinetic frictional force is no longer constant. The value that we just calculated, the y, we want to give a reason. So basically what is happening is as the block is moving towards this direction, it means it's moving closer to the pulley. That means this angle here, the 15 degree angle, is going to increase. It's going to grow bigger. So as it increases, that is obviously going to affect the Ty, the vertical component of the tension. It is also going to increase as the angle is increasing while the block is moving closer to the point C. This angle here will increase, causing the vertical component of T to increase. But what does the vertical component of T has to do with that? So obviously, as the vertical component increases, that will affect the normal force. And apparently, the kinetic frictional force is dependent to the normal force because Fk, by the way, is equal to mu kn. So since the kinetic frictional force is dependent to the normal force, obviously the change in the normal force will result in the change in the kinetic frictional force. What has caused the change in the normal force? It is the change in the vertical component of tension. And what has caused the change in the vertical component of the tension? It is the change in the angle between the tension and the horizontal. We can just simply say in the horizontal increases or changes, we are answering. So I was just trying to add more flesh to explain further on that. So give a reason for this statement. We are simply saying the angle between the string and the horizontal changes, or we simply say it increases. Right, let's go to the next question. The horizontal surface on which the 8 kg block is moving is replaced by another horizontal surface made from a different material. Will the kinetic frictional force calculated or not? Give a reason for the answer. Our answer lies on the same statement we brought out, the same equation. Fk is equal to mu k times n, where mu k, the coefficient of kinetic friction, is representing the nature of the surface or the texture of the surface, right, upon which the object is moving, right? So once the surface changes, obviously mu k will change. Will the kinetic frictional force change? Yes, it will change. So we are saying yes, it changes. Give a reason. It is because the coefficient of kinetic friction changes as it depends on the nature of the surface. So we can also say it is because the coefficient of clarification of force mu k changes, right? So that's 2.5 for us there, right? Let's quickly go to the next question, right? The next question here is saying a minibus takes traveling south at a velocity of 20 meters per second collides head-on with a car of total mass 1,248 kgs, including the driver, heading north with a velocity of 15 meters per second. After the collision, the vehicles move together at a velocity of 10 meters per second south. Right. There we have our text. Of course, they are the diagram. State the principle of conservation of linear momentum. Right. So it simply states that the total linear momentum of an isolated system remains constant, or we can simply say it is conserved. The total linear momentum of an isolated system is conserved, or the total linear momentum of an isolated system remains constant. That's 3.1 for us. Let's go to 3.2. The driver of the car claims that the taxi was not only speeding, but it was overloaded with passengers. Consider the information below. Mass of the empty taxi was 2,000. Average mass of a person 70 kgs. Maximum legal occupants of the taxi is 12 people, including the driver. Right. Use the principle of conservation of linear momentum to determine how many passengers exceeded the legal limit for the taxi. Assume all passengers are of average mass. Right. Here is what we can do to answer this question. Number one, the principle of conservation of linear momentum simply tells us that sigma of pi is equal to the sigma of pf, which means the algebraic sum of the momentum, the initial momentum, is equivalent to the algebraic sum of the final momentum, right? So with that in mind, we can directly say MA wanting just to choose, it's my option to just use MA VAI plus MB VBI, where I am saying A is my taxi and B is my car, right? VBI is equal to, now because they collided and they moved together, we can now say MA plus MB bracket VF. We are now saying they have moved together after the collision. Okay. So this is the situation that we now have. By the way, I'm going to take south as positive. Take south as positive. It is the choice that I have made as positive. Right, then we list the data that we are having from the information that we have been given. Right, number one, we have, I am calling my text. So we can call it empty VT. It's to one and the same thing. It's just my choice that I want to call this A. I want to call this B. So MA becomes the unknown mass, right? Then VAI, the initial velocity, it becomes the initial velocity of the taxi. It is 20. Apparently, we have taken south as positive, so it is indeed 20 meters per second. Then MB, remember, mass is a scalar component. It doesn't have a direction, so because of that, it cannot be negative. Right, so our mass of the car, which I have labeled as MB, is 1,248 kgs. Right, then VBI becomes negative 15 meters per second. Why? Because I chose south as positive. So the car is going to the north. So because of that, it becomes negative. Then finally, VF, the final velocity of the two, is now positive 10 meters per second. Why positive? Because they went to the south after the collision. When they are now moving together, they are now going to south, so it is positive, right? So with that in mind, we now come and substitute the information that we have. Apparently, we don't have MA, the mass of the text. What we just have is the mass of the empty text and the average mass per person, right? So we want to first find the total mass of the overloaded text, right? So MA apparently is representing the total mass of the overloaded text, which is including the net mass of the text, which means before it has before it has any passenger within it. So that's the 2,000 kgs is included in that, together with the passengers, all of them that are there, right? So MA multiplied by, we can now substitute the information that we have multiplied by 20, so we know that it's positive. Now we have listed our data. I always advise that we do so. We list our data, it saves us very well. Then multiply by MB, which is 1,248 times negative 15. Remember, it's going to the north, is equal to MA. It is the one we also don't know, we do not know it, so just say MA plus MB, we know it, 1,200, what? 1,248, right? Multiply by 10. Right, so hence we can simplify. MA times 20, that's 20 MA, right? Plus 1,248 times negative 15, so that becomes negative. So we are saying minus, plus minus, obviously it's going to be negative 18,720. We just punch that on the calculator, right? Is equal to, right, 10 times MA, we get 10 MA, right? 1,248 times 10, we get 12,480, right? Variables to one side and constants to the other. We end up having 20 MA minus 10 MA is equal to 18,720 plus 12,480. There we are, right? So simplifying that, it's going to give us 10 MA is equal to, right, 18,720 plus 12,480. That obviously is going to give us 31,200. We just punch that on the calculator. Divide by 10. Divide by 10. So MA is going to be equal to, right, that's 3,120. Okay, so 3,120 becomes the gross mass of our minibus text. So first things first, let's subtract now the net mass of the text. 3,120 minus 2,000 before it doesn't have, it has been loaded. So what do we end up having? We end up having 1,120. So the 1,120 is now the mass of all the passengers, including the driver. So we now say the average mass of each person is 70 kg, remember, 70 kgs. So we simply say now 1,120 divided by 70. Why? To ascertain how many people were in the text. So we will get 16. So it means we have 16 people, right? So if there are 16 people, there were 16 people, the taxi is supposed to carry how many people? 12. So they had exceeded with how many? Therefore, 16 minus 12, and that will give us obviously 4. So it means therefore it had exceeded with what? With 4 passengers. So we can indicate that now. So it had exceeded with 4 passengers, 4 people, right? So this is the number of the people who had exceeded. It caused the text to be overloaded. And let's go to the next question. The next question there is saying 2.3, 3.3 actually. Do the necessary, okay, use the principle of conservation. Okay, that's the question we've just answered there. Do the necessary calculation to show that the collision is inelastic. First things first, what is an inelastic collision? So an inelastic collision, it is a collision in which the total linear momentum, of course, is conserved, but the total kinetic energy is not conserved. So that's an inelastic collision now, right? So with that in mind, it means we want to check, is there a change in the total kinetic energy. So we want to first calculate the total kinetic energy before, and we calculate the total kinetic energy after. So if it is an inelastic collision, we say sigma of EKI should not be equal to the sigma of EKF. As a matter of fact, sigma of EKI must actually be greater than the sigma of EKF, right? So with that, let us first calculate the sigma of EKI, the sum of the kinetic energy before. So in calculating it, we are saying half MA VA squared plus half MB VB squared. Remember, I had called the text my object A and the car my object B. It's just a choice that I did. It's not like it's something that has to be always like that. It's just me who thought of just calling the text A and the other one B. Right, so I calculate this. So I'm going to have half multiplied by, now the mass of the text is now known. It's the overloaded text, 3,120. That's the one we are using. Multiplied by 20 squared, right? Plus half 1/2 multiplied by MB. That's 1,248 times that's 15 squared, right? And that definitely gives us 764,400 joules. That's our kinetic energy, this total kinetic energy before the collision. Now let's go to the total kinetic energy after the collision. We call it sigma EKF. We want to check what are we going to get again. We are saying it's half MA VAF, apparently MB, right? VB, MAVF VA squared plus half MB VB F what squared. But do remember VBF and VAF, they are the same. So we can just say half MA bracket MA plus MB multiplied by VF squared. It will still be correct to say half bracket MA plus MB bracket times VF squared. Will still be correct. It's not a problem, right? So I have half multiplied by 3,120 times 10 squared plus half multiplied by 1,248 times 10 squared, and that will now give us 218,400. Right, so we are now comparing that joules. Right, so we are now comparing. What are we noticing? We notice that the sigma, the total kinetic energy before, is no longer the same as the total kinetic energy after. And as a matter of fact, just out of interest, we need to know that this is because in an elastic collision, the energy is obviously converted, the kinetic energy is converted to other forms of energy, e.g. heat energy, sound energy, etc. So due to that, it means we are noticing that, therefore, the sigma of EKI is not equal to the sigma of EKF. Therefore, we are saying it is what? It is not, it is inelastic. We have drawn a conclusion, right, using a calculation. So we are saying, therefore, it is inelastic. Right, 3.4. Modern cars have seat belts, airbags, and crumble zones to help minimize injuries during accident. Mentioned above contribute to the safety of passengers. Right, is we are using the equation F net, of course, is equal to the change in momentum over the change in time. We can still refer to that. Right, so with that in mind, we can say during a collision, the crumple zone or the airbags, the impulse remains constant, or we can say the change in momentum remains constant. So of course, it's going to remain constant during the collision. Then, but the contact time increases. What is causing it to increase? The chromosome or the airbag, right? And when it increases, this decreases the net force because the two are varying how inversely. So we are saying from the equation, for example, F net is equals to change in momentum over the change in time. So time and F net, they vary inversely. So when the time increases, obviously F net will decrease. So we are saying during the collision, the impulse or the change in momentum remained constant, and the time increases. And when the time increases, the net force decreases. So we are just indicating that. So from the equation, F net is equal to delta P over delta T that I'm just indicating there. Right, so we have answered this question. Let's go to question number 4. Question number 4 is saying ball A is dropped from a balcony 19.6 from the ground. At the same time, an identical ball B is projected vertically downward from the top of a building 29.6 meters from the ground. Right, as shown below on the diagram below. So there is our diagram. Now the ball hits the ground. The balls hit the ground simultaneously. Ignore the effects of air resistance. 4.1. Write down the acceleration of ball A at the moment it is dropped from the balcony. Right. So apparently these are projectiles. So the acceleration is known, right? And the acceleration is 9.8 meters per square second, and its direction is also known. It is always acting downward because the only force that is acting is what? Gravitational force. So we'll simply say 9.8 meters per square second downwards. So even the direction, we know it, right? So that's downwards there, right? Downwards. Right. Let's go to the next question. The question is saying, calculate the velocity 4.2.1 with which the ball A, with which ball A is the ground. Right. So for ball A, taking downwards as positive, it has been dropped. So wanting to take downwards as positive, it means if I list the data for that ball A, right, number 1, we have the VI, it's 0 meters per second, it's 0, right? And then we are calculating VF apparently for ball A, right? And in delta Y, the height from which ball A was dropped is 19.6. It's going to be positive because we have taken downward as positive, right? And again, we have A, the acceleration is acting downwards. It's known, it's 9.8 meters per square second because we are dealing with a projectile, right? So it's positive as well. So with that in mind, we then go to the equations of motion to choose which equation. So we can use VF squared is equal to VI squared plus 2A delta Y, right? So apparently that's VF squared. VF we are looking for. So VF squared is equal to 0 plus 9 plus 2 multiplied by 9.8 multiplied by 19.6, and that gives us 384. So we are saying VF squared is equals to 384.16. So square root both sides, it means VF is going to be equal to 19.6 meters per second. That becomes our velocity. So the question simply said, calculate the final velocity. So we need the magnitude and also the direction. So right now we just calculate the magnitude. So what then shall be the direction? It's downwards. So it's 19.6 meters per second downwards. That becomes our direction. Because remember, velocities are vectors. They have both magnitude and what? And direction. So we have calculated 4.2.1. Right, with that having been done, 4.2.2 is now saying calculate the velocity with which B must be projected to reach the ground at the same time as A. Right, what do the both balls, ball A and ball B, share in common? They share the same time because they were thrown at the same instant and they both hit the ground simultaneously. So due to that, the same time that ball A took to hit the ground apparently is the same time that ball B will also take to hit the ground. So with that in mind, we can first calculate the time that ball A took to hit the ground. Then we will know that that's the same time that ball B will also take to hit the ground. So still having our downward as positive, it means we can choose the equation VF. So for the sake of time, I won't list the data there. I'll just go straight. VI plus A delta T is the equation we can use to determine the time now that we have the final velocity of ball A. Remember, we are using ball A to identify the time. Why ball A? Because we know it is the same time as the time for ball B. So we are saying 0 plus 9.8 delta T. So that's 9.8 delta T is equal to 19.26. Therefore, divide by 9.8, divide by 9.8. So we end up having delta T being equal to 2 seconds apparently. All right, so this is the time that it takes for ball A to hit the ground. Apparently, this is also the time for ball B. So we take that time and we go to ball B to try and ascertain or try and identify the velocity that ball B was projected with. So using the equation, delta Y is equal to VI delta T plus half A delta T squared. We can still identify it, knowing very well that it's not the only option we have, of course. So what is the height at which Bobby was thrown? That's 29.6 is equal to VI, which we don't know. That's the velocity we are looking for. Multiply by 2. By the way, it becomes very important again to be able to identify what exactly is it that you are looking for. Is it VI? Is it VF? Exactly what is it? It makes it a little bit easier. So half times 9.8. Remember, we have taken down one is positive. So multiplied by 2 squared. And as a matter of fact, time is a scalar. It doesn't have, or it can never be negative as well. Okay, so that should also serve as something that can help you. If you ever calculate time and you determine it as a negative, it's a sign alone that there is somewhere you made a mistake. So you just go back into your working and check where could you have possibly missed it. Right, so simplifying that, we end up having 29.6. So I'm just trying to show all the necessary, all the working actually, so that we can just follow what is happening. 2VI plus, so if I multiply that, I get 19.6. So transposing that, 29.6 minus 19.6, I get a 10 there. 10 is equals to 2VI. Divide by 2, divide by 2. So VI is equal to 5 meters per second. Also, because the ball was projected downwards, this is a velocity towards the ground, so it is downwards, the magnitude and the direction as well. So we have simplified here. We got our velocity as such. Right, then the next question is now saying, on the same set of axes, sketch the velocity versus time graph for each ball A and B for the entire motion. Take downwards as negative, which means if we are taking downwards as negative, we are taking upwards as positive, right? So with that having been said, how is the graph going to come out? So here is how the graph will be like, right? Number one, we have on the vertical axis our velocity shall always be placed on the vertical axis. So we say V in meters per second. Right, that's our velocity there. Then we have our time in seconds in the horizontal axis, time in seconds. Right. Then we have our A, right. It was dropped, so its initial velocity, remember, it's 0. So we start here directly, there we go. That marks A. Then it took how long to hit the ground? The time it took 2 seconds. So we shall indicate our 2 seconds here, and of course our 0 here. Right, that marks A. So we label this graph as A. Then B started with a velocity of 5 meters. So taking downwards is negative. It means we are going to start with a negative 5 meters per second. So there it is. That's ball B now. But it also hit the ground at the same time as ball A. So this becomes the graph of B. Mind you, these are dotted lines that I'm having here on the vertical X, on the vertical line there. Right, so that's B there, sharing the same time with ball A. So that's A, that's B. This is our graph. If we take downwards as negative, right? So we have answered this question, right? So our next question, right? Our next question, now we are in section A. Question 1, multiple choice questions. 4 options are provided as possible answers to the following questions. Each question has only one correct answer. Write down only the letter A to D next to the question number in your answer book. Which one of the following is the IUPAC name for the compound below? Right. So number 1, we are seeing this is a saturated compound, but apparently we see that there is a halogen there. Right. So we want to first identify the longest chain. So apparently this is the longest chain that we are having, the longest continuous chain of carbon atoms. So this is the longest chain that we are identifying here, this one, right? So it means it has left us with a substituent there. We have alkyl groups, we have a branch here, we have another one here. So each of the ones that we have, they consist of one C atom. So this is a methyl, this is another methyl, and apparently they are tied to the same carbon atom. So what we want to try to do is to try and minimize our numbers to be as small as possible. Right, so what do we do? If we try to count from this direction, we want to locate the position of our substituent and our branches there, of course. So we have, if we try to count from this direction here, if we try to count here, from here, it means we have 1, 2, 3, which means this one is on the position 3, and these 2 are on position 4. So we have 4, 4, and then we have 3. But how about if we start from this direction? If we start from this direction, this end, it means we have 1, 2, 3, which means these 2 are on 3, 3 because there are 2 of them. So it becomes a di. It's 3, 3 dimethyl, of course. Then how about this one? It becomes a 4. So if we try to add now, 4 plus 4 plus 3, of course, it's a bigger value than 3 plus 3 plus 4. So we start from this direction, therefore. This is the direction we are going to start from. As a matter of fact, the longest carbon chain that we have identified, 1, 2, 3, 4, 5, 6, happens to have 6 carbon atoms. That makes it to be a hexane. So we have a hexane there, right? And then we have identified that our alkyl groups are actually having 1 C atom each. So they are methyl. So since they are 2, they become dimethyl. So it means we are having 3, 3 dimethyl. Then we have a chloro, which means we have a chlorine atom there. So we start with chlorine always because it starts on the in alphabetical order. So we can now say 4 chloro, right? Chloro, then 3, 3, that's methyl hexane, right? So that is matching number 1.1 D apparently. So 1.1 is D. That's what it means. All right. So we have identified 1.1 is D. Let's go to 1.2. Right. For 1.2 is saying which one of the following compound is the highest boiling point. Right. So from the look of things, all the compounds that we see there are actually alkanes. All of them, they are saturated organic compounds, and the hydrocarbons as a matter of fact. So now, which one is the highest boiling point? Now, since all of them are alkanes, the one that has the highest boiling point is actually the one with the longest chain, and the one that is the longest chain is the one with the biggest number of C atoms, of course, in this regard, because they are all forming straight chains, right? So we see that this one here, at C has 1 plus 3, which makes them 4. Then that's what 5 there. But the rest, of course, they are having 1, 2, 3, 4, 1, 2, 3, 1, 2. I'm counting the number of C atoms. So due to that, it means C is the longest chain of them all. Do kindly take note CH2, CH2 bracket 3 simply means CH2, CH2, CH2. That's what it means. So we are having 3 carbon atoms already. Those are 3, plus the other 2 that we already have there, they become 5. Right? So our answer then is 1.2, it's C. So this is our answer. It is the one with the highest boiling point because it is the longest chain. It is the longest chain length. It is actually the biggest chain length. At 1.3, it's saying consider the cracking reaction below, right? Determine the correct values of X, Y, and CR respectively. Right. By the way, it just might interest us to know what a cracking reaction actually does. It's a chemical reaction that results in the breaking down of longer chain alkanes to form shorter chain alkanes that are often useful. We are saying often the longer chain alkanes, such as crude oil can have even a maximum to occasionally have up to even 40 C atoms. As an example, so in that form, it has less uses, or it actually doesn't have much uses. It's not that useful. So it has to be broken down into shorter chain alkanes that are useful, e.g., octane. It becomes useful now, right? So here we are. What's happening? We are having our longer chain alkane. Apparently, we are seeing that it's an alkane. Even the general formula also should also be known of alkanes, right? So, what has happened during the cracking, which happens also in 2 types of reactions: thermal cracking or catalytic cracking. Right? So we are saying, I'm just passing through that, no one is asked, I'm just digressing to explain that also in the process. So we are saying this is an alkene. So during the process, an alkene and a shorter chain alkene are formed. So C3H6 is telling us that this is an alkene because the general formula becomes CnH2n for alkene. So that's an alkene then. This, the one we are seeing, and it's the propane, right? But this one here, C3, because we expect a shorter chain alkane to be formed. So if it is C3, H should become, from the general formula of alkanes, should become 2 times 3 plus 2, and that gives us 8. So we have already identified X as 8 because we are expecting this to be a shorter chain alkane from our understanding of what a cracking reaction is. Then here we now see 2CyH2, right? To identify Y, now we are checking how many C atoms are left. So we have 3 here, we have 3 here, in order for them to be balanced with the ones we have on the left-hand side, the ones on the left-hand side are 10. So we expect these remaining to be 4, because 3 plus 3, that's 6 C atoms. So the remaining, for us to get a balanced, to have a balanced equation, there are 4. So Y should become 2, so that we say 2 times 2, the C atoms become what? 4. Y is 2. And then Z is the remaining number of H atoms from where? From 22. Because we need the same number of C atoms on the left-hand side as to those on the right-hand side. We need the same number of H atoms on the left-hand side as to those on the right-hand side. So if there are 22 here, we have already seen these are 6, and these are also 8, as we have seen. Now, it means from 6 plus 8, subtract from 22, we are left with, again, 8. So, again, we are saying 2 times Z. So we are saying 2 times Z is equal to 8. So if we divide now by 2, divide by 2, we get Z being equal to what? 4. That's exactly what we also did at Y there. We are saying 2 times Y is equal to the remaining number of C atoms, which were 4. So divide by 2, divide by 2, so it means Y is equal to what? To 2. So therefore, our X is 8, our Y is 2, and our Z is actually 4. So 1.3 becomes C. We have identified them. Let's quickly go on to the next question. Right, our next question there is saying, the letters A to F in the table below represent 6 organic compounds. Okay, right. Is compound C saturated or unsaturated? Right. What we see there at compound C is a condensed structural formula. So a condensed structural formula is simply a formula, a structural formula that is no longer having the lines that are representing the bonds that are between adjacent atoms. So on what we are witnessing then, this is an unsaturated organic compound. It is a hydrocarbon, as a matter of fact, and just out of interest, that's an alkyne there we are having. So that's unsaturated. Give a reason, right? Our reason lies on our understanding of what a saturated and unsaturated organic compound is. So it might interest us just to pass through that to know that a saturated organic compound, it is a compound that consists of only single bonds between its adjacent C atoms. So that one is not consisting of only single bonds. So unsaturated now, it means it has more than one bonds, which means it can have double, it can have even triple bonds, right? So that's an unsaturated. We are giving a reason now. It is because it consists of a triple bond, or it has more than one. It has more than one bond on adjacent C atoms, right? So we have answered that in 2.1. So we are saying it's unsaturated because it has triple bonds. 2.2.1, write down the letter that represents each of the following. So basically, we are being tested on our knowledge or understanding of the nomenclature of organic compounds. So we are saying, write down the name of the letter that represents the following in ester. So in ester, we see here butyl propanoate. That's an ester, the D. Then 2.2.2, functional isomer of butanol. What is a functional isomer? Functional isomers are compounds that have the same molecular formula but different functional group, which means they belong to different functional groups. And as a matter of fact, butanol is an aldehyde. So aldehydes usually form functional isomers with ketones that have the same molecular formulae with them, right? So in that regard, we are saying we are looking for a ketone there, which has 4 carbon atoms. Why? Because but means it has 4 C atoms, and now its suffix means it's an aldehyde. So due to that, we are looking for a ketone that has 4 C atoms. Apparently, we see this is a ketone here. It is butane 2-on, and obviously it becomes what? The functional isomer of butanol. So our answer there is B. That's the letter that is represented. So we said this is B, right? Let's go to 2.2.3. A compound with the general formula of CN2N plus 2. So CnH2N plus 2 is actually the general formula of alkanes. So if this is the general formula of alkanes, we are simply looking for an alkane there. And from the look of things, A is actually an alkane. And it is actually having 1, 2, 3, 4 carbon atoms. That's butane then. So that's our compound that is the general formula of CnH2n plus 2. Then the next question, 2.2.4, is now saying a compound used as a reactant in the preparation of compound D. What is compound D? That's butyl propanoate. So how are esters formed? Esters are formed from alcohols and carboxylic acids. So we are looking for an alcohol or a carboxylic acid. So from even the name of the ester, we can even identify the alcohol and the carboxylic acid. Butyl, this is the alcohol. And the propanoate, that's where the name of the carboxylic acid is. So the carboxylic acid must have, prop must have 3 carbon atoms. But the alcohol must have 4 carbon atoms. So from the look of things, it means what we are looking for here, E best fit our description. So we are saying for 2.2.4, we see butanol there. So that's an alcohol. Apparently, we do not see propanoic acid because that's the other one that we are using, the organic acid that we use to form a butyl propanoate. So that it means the compound that is used as the reactant in the preparation of compound D is E. We've answered that. Then 2.3.1, write down the structural formula of compound D. So we want the structural formula of that compound, right? So here is what we are to do. Remember, we are saying it's formed, butyl propanoate has been formed from an alcohol, and this is forming the alcohol, and it's always like that. And this is our acid, our organic acid, the carboxylic acid. So I'm going to start, of course, with the alcohol here. 1, 2, 3, 4, right? Then I indicate my carbon atoms then. My hydrogen, okay, my hydrogen atoms need in indicate that it is, okay. Okay. Okay, so there it is, knowing that this is our alcohol, our butanol, and this is our carboxylic acid, our propanoic acid, right? So together they have reacted to give us the ester butyl propanoate. Okay, let's go on to the next question. The next question is now saying 2.3.2. This compound E, that's an alcohol. To which functional group do alcohols belong? They belong to the hydroxyl group. So that's the hydroxyl. 2.3.3. The IUPAC name of the positional isomer of compound E. We are saying it is our functional group that must actually change its position. So which other compound can we have? So it's going to be butane 2O. If we just move, so we end up having butane 2O, right? That becomes the positional isomer of compound E. Okay, they said name of the functional group of compound E. We brought it out, and then IUPAC name is the one we just brought out. Structural formula of the chain isomer of compound A, right? 10 in passing, compound A, that's butane. So what is its chain isomer? Again, it might interest us to note the chain isomer, or chain isomers actually compounds that have the same molecular formula but different chain length or chains. So in this case, we are having good example, 2-methyl propane. So they want the structural formula, so we just indicate the number of carbon atoms, right? Then we have our C atom there, right? So there we are. That forms the structural formula of our chain isomer for that compound. So there it goes. There it goes. There it goes. Remember, it's a saturated organic compound, so we must indicate it with all single bonds throughout. That's our our saturated hydrocarbon there, right? 2-methyl propane. We want the structural formula only, right? Then the next question is now saying, for compound F, write down the homologous series to which it belongs. So compound F is actually, it's having halogens there, that's bromine. So because of that, it belongs to the haloalkanes, or it belongs to the alkyl halides. So that's it. That's the IUPAC name of, that's the homologous series to which it belongs. Then the IUPAC name of it. Right, so first things first, again, we identify the longest chain, and apparently the longest chain that we can have is this one, the longest chain of carbon atoms. Apparently, it is going to be this one. That's the one we have there. So there it goes, 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 there it goes. We're just circling the carbon atoms there. There we go. Right, so how many C atoms are we going to have there? 1, 2, 3, 4, 5. Now, because of these two that we are witnessing here, it means there are 2, which means 5 plus 2, that's 7, plus this one, there's 8. So it means that forms an octane. That's the parent name there. So, and then we have bromine, one bromine atom and the other one. So we try to minimize, trying to have our numbers to be as small as possible. So it means we have to come from this direction. 1, 2, 3. So it becomes 3, 5. So let's write the name down. So that's 3, 5 hyphen dibromo. So that's dibromo octane. That becomes our name, octane. Right, remembering that between every number and the letter, we must place our hyphen there. And so there it is. That's our name. Then write down the balanced chemical equation using molecular formulae for the complete combustion of A. Compound A, we have seen that it's butane. So what is its molecular formula? Butane has 4 carbon atoms. So a molecular formula is simply identifying or showing us the number of atoms that are in the compound. So we see it as C4H10. It is right. So when it undergoes complete combustion, it means it is burning in excess oxygen. So it means we are having octane, we are having it butane burning in excess oxygen. What are the products? So the products are carbon dioxide and water. Right? It might interest us the other, to note that the other, just out of interest, that the other product that is formed is also energy. Heat energy is also produced there as a product, right? So this is the equation, but it's not balanced. So we want to balance it now. Now in balancing, we start with all other atoms. We should always end with the oxygen atoms. So we can start with the C atoms here. There are 4 this side. We want them also to be 4 there on the right hand side. So we add a 4 here. Had we say, for example, if there was a 2 there, we were supposed to say 2 times 2, which means we're going to balance with the 2 here. So there we are balancing with the 4. We're done with the carbon atoms. Let's go to the hydrogen atoms. H atoms are 10 this side on the left hand side. How many are they on the right hand side? There are 2. So in order to balance them, we need a 5 here. So that 5 times 2 is now giving us a 10. So the H atoms as such, they are also balanced. Right, let's go now to the O atoms. They are the last ones. Right, so the O atoms, we see that there are 2 this side. Apparently, how many are they now on the right hand side? There are 4 times 2, which means we have 8 here, and 5 times 1, of course, there are 5 here. So 8 plus 5, that's 13. So we have 13 O atoms on the right hand side. So in order to balance them now, because there are 2 on the right hand side, we have to use 13 over 2, half of that 13. Now we are not allowed to balance with decimals or fractions. So if we can indicate it as a fraction like this, it becomes easier. We have just simply multiply throughout by the denominator there. So we now multiply here by 2, multiply here by 2, multiply here by 2, multiply there again by what? By 2. So we end up having 2C4H10 there plus 13 or 2. So this 2 and this 2, of course, they are cancelled each other, 2 into 2, 1 into 2, 1 there, right? Giving us 8 plus 10 H2O, our water, right? So this is our complete combustion of butane in excess air or in insufficient oxygen. So this is what is happening. So we are done with this question. We quickly go to the next question. So our next question is now saying, okay, question 3, study the vapor pressure versus temperature graph for 3 organic compounds X, Y, and Z below, which belong to different homologous series. Atmospheric pressure is 100 kilopascals. So that's what we have been told. We've been told that our atmospheric pressure is 100 kilopascals. As a matter of fact, atmospheric pressure is the pressure that the air or the atmosphere exerts on the Earth's surface, right? Matt just simply has to pass through that. Right, write down the vapor pressure of compound Y at 90 degrees. So this is just an interpretation of the graph that is being expected of us. So I'll try to enlarge it a little bit so that I explain, right, how we are getting there. Right, so what is happening is, if our scale is 25, 50, 75, it therefore means this is 5, 10, 15, 20, 25. Therefore, we are saying this is 75 here, this is 80, 85, this is 90. So what we want is the pressure for Y at 90 degrees Celsius here at this point. So we want this pressure that is corresponding with the 90 degrees Celsius, right? So what is it? We take our ruler, we draw a vertical line against 90, we draw a horizontal line towards the vertical axis. We notice that it's going to tally with 150 kilopascal. So it's just a matter of interpreting our scale properly. That's what the question was actually interested in, right? So we've indicated that, right? We can go to the next question. Right, so our next question is saying the graphs can be used to determine the boiling point of the 3 compounds. Define boiling point. Remember there the instruction, the indication it told us that the boiling point is 100 kilopascals, right? Define boiling point. Boiling point by definition is the temperature at which the vapor pressure of a substance equals the atmospheric pressure, right? Or the vapor pressure of a liquid equals the atmospheric pressure, right? What is vapor pressure? It is the pressure exerted by a vapor at equilibrium with its liquid in a closed system, right? And of course, I mentioned the atmospheric pressure, then passing that is pressure that the atmosphere or the air exerts onto the Earth's surface, right? That's 2.2. So I just digress to explain other things that are not being asked by the question. Determine the boiling point of X. Remember, the boiling point, we had been told that atmospheric pressure is 100 kilopascal. So when the vapor pressure is equal to 100 kilopascals, that's when we have reached the boiling point. So what we simply do is we go for X, we simply go at 100, draw a line with a ruler straight until we reach X, then we go down. So remember, each small unit there, it's 5. It's each small, according to the scale there, that's 5. So this is it means therefore this is 55 degrees Celsius. So it means we know the boiling point of X, that's 55 degrees Celsius. Right, then The next question, 3.3, is now saying the homologous series to which the three compounds of similar molecular masses belong were identified in random order as alcohol, carboxylic acid, and then a ketone. Which compound X, Y, or Z is a carboxylic acid? Now, among these organic compounds that have been given, the one that we have the highest boiling point and of course the lowest vapor pressure, because vapor pressure varies inversely, of course, with the boiling point. The one that we have the highest boiling point there, apparently, it will be the carboxylic acid. So from the look of the graphs, it means graph Z is the one that we have the highest boiling point and apparently the lowest vapor pressure. So due to that, our carboxylic acid is graph Z. That's our carboxylic acid. So it's Z. We have identified it. Right. Explain the answer 3.3.2. Explain the answer to question 3.3.1 by referring to the type of strength of intermolecular forces and compounds of each of them are homologous series above. Right. It might interest us to know that among all the organic compounds, alcohols and carboxylic acids apparently are the ones that have the highest boiling points, the two of them. But carboxylic acids have a higher boiling point than alcohols due to the fact that carboxylic acids have two sides for hydrogen bonding, and alcohols have only one side for hydrogen bonding. So due to that, we are saying our carboxylic acids have a higher boiling point. We can also say carboxylic acids are capable of forming dimers. A dimer, alcohols actually cannot. Right. So let's now explain. Want to put that in writing. Number one, we shall say, first point, carboxylic acids have two sides. So we are saying carboxylic acids have two sides for hydrogen bonding between molecules. Secondly, alcohols, we are now explaining now. Alcohols have one side, so alcohols have one side for hydrogen bonding between molecules. Then ketones have dipole forces between molecules, right? What exactly is happening is we have to mention the major reason why carboxylic acids will have a higher boiling point, a lower vapor pressure than the rest of the compounds that we've been given. So the major reason is because, of course, these two have hydrogen bonds, but carboxylic acids now have two sides for hydrogen bonding, unlike alcohols, which have one side for hydrogen bonding. So in as much as they have the strongest intermolecular forces, nonetheless, carboxylic acids have a higher boiling point now than the alcohols due to the reason mentioned above. So we are now putting that in writing now. And then we then say, therefore, carboxylic acids have the strongest intermolecular forces, and therefore, most energy is needed to overcome intermolecular forces of carboxylic acids, hence the lowest vapor pressure we have explained. So 4 points specifically to support the reason why we are saying Z is a carboxylic acid. Right. Let's go to 3.3. Compound X has 3 carbon atoms per molecule. Write down the IUPAC name of compound X. Remember, compound X is the one with the highest vapor pressure, which means it has the lowest boiling point, because the vapor pressure and the boiling point, they vary inversely. So among these three compounds, we have the ketones, we have the lowest boiling point and the highest vapor pressure, followed by alcohols, and then lastly, carboxylic acids. Right, so due to that, we are saying X is a ketone, and since it has 3 carbon atoms, that means it is now propanol. That's our ketone, right? So we have indicated it. Then let's go to the next question. The next question is now saying, the flow diagram below shows how an alcohol compound P can be used to prepare other organic compounds. The letters A to E represent different organic reactions. X, Y, and Z are organic compounds, right? Is P a primary, secondary, or tertiary education, tertiary alcohol? Give a reason for your answer, okay? 4.1. Is a compound P a primary, secondary, or tertiary alcohol? And apparently, it is a secondary alcohol. Why? Because the carbon atom bonded to the OH group or to the hydroxyl group is also bonded to two other carbon atoms. So due to that, we are saying it is a secondary alcohol. That's how we identify that is it a secondary, a primary, or a tertiary alcohol. That's what we do. Right? Pardon my sarcasm there. Pardon my joke. Right? We're just saying it's a secondary alcohol because the carbon atom bonded to the hydroxyl is also bonded to two other carbon atoms. So 4.1 we've answered there. Let's go to 4.2. 4.2 is now saying reaction A is an example of a dehydration reaction. So of course, we have been told that. And as a matter of fact, dehydration is a type of an elimination reaction. Explain what is meant by the term dehydration. So, in simpler terms, dehydration, it is simply a reaction in which water is removed from a compound, right? It is a reaction in which water is eliminated or is removed, right? Write down the name of the catalyst required for reaction A. Apparently, there's a need for a catalyst there. So the instruction again, we should be very cautious. They say the name, not formula. So we want the name. So our catalyst is either sulfuric acid. We can use concentrated sulfuric acid, or we can use phosphoric acid. So we can indicate sulfuric acid, or we can use phosphoric acid. We'll still be okay to say that. Okay, so let's go to the next question. It's saying, write down the type of addition reaction represented by E. So indeed, E is an addition reaction because a reaction in which alkenes undergo to form saturated organic compounds, obviously, it's an addition reaction. But what name is that addition? What is being added to the alkene? We are adding hydrogen. So that's hydrogenation because we are adding hydrogen. So that's hydrogenation there. And since it is hydrogenation, we need a catalyst. We can use platinum, we can use palladium, or we can use nickel, any one of them. All right, so that's in our question number 4.3.1. 4.3.2, elimination reaction represented by D. So this is now an elimination reaction again. Let's trace it from the alcohol compound P. So compound P underwent a reaction, HBr. Apparently that's a substitution reaction. So HBr to form compound X. So compound X is a halo alkane. We traced it from that alcohol. The reaction in which alcohols react with hydrogen bromide, it forms an halo alkane. That's where we came to know that this is a halo alkane that we are dealing with here. So the halo alkane now has undergone a reaction to form an alkene, but during the substitution reaction, it means the substitution that was done was for HBr, hydrogen bromide. So it means our halo alkane is having a bromine atom, right? So, and hydrogen. So it means obviously when it is now undergoing elimination reaction, this is dehydrohalogenation, where we are now eliminating the hydrogen in the halogen atom. right? So this is dehydrohalogenation. You can also call it debromination. It's called dehydrobromation or dehydrohalogenation. Okay, so that's 4.3.2. Let's go to 4.4. 4.4 is saying sodium hydroxide is used as one of the reactants in C. So likewise, yellow alkanes can still also undergo an interconversion to also form alcohols under a substitution reaction, specifically under hydrolysis. So the question there now is asking, what type of reaction takes place? Apparently that's a hydrolysis or that's substitution, where yellow alkanes are now undergoing a reaction to form alcohols. So that's a hydrolysis. It's a substitution reaction, and it must take place in the presence of water or of a dilute strong base. Dilute strong base, such as the sodium hydroxide that we witnessed then, right? So state the two conditions, reaction conditions for this reaction. Number one, we need a dilute strong base, or we can be specific since they said sodium hydroxide is used. So we'll say dilute sodium hydroxide. So we use the sodium hydroxide, dilute sodium hydroxide, or we may need water, but of course for this reaction, since we have used sodium hydroxide already, dilute sodium hydroxide already is the one we need to indicate. So we need dilute sodium hydroxide, and we also need moderate or mild temperatures. Mild temperatures, right? So we need dilute sodium hydroxide or dilute strong base, and we also need mild or moderate temperatures, right? Those are the reaction conditions. We need two of them, right? 4.3, write down the IUPAC now, because what is happening is the OH is the one that is being substituted by BR. And obviously the OH will now substitute the BR to form water H2O, right? So that's what is basically happening there. They are substituting each other. So because of that, HC and also HBr are reacting. Obviously, that's what is going to be formed by the yellow alkane. So with that in mind, it means the structural formula of that, the IUPAC name, of that compound X is going to be 2-bromobutane. Why? Because this alcohol here is in butane 2O. So since it is butane 2O, obviously when we remove the OH group, when we remove the hydroxyl group, it means obviously that's where we end up having our when we substitute, actually, that's when we are going to end up having the BR located. So it's going to be 2-bromobutane. That becomes the name of our compound X. Right, the next question now, 4.4.1. 4.5, right? It's saying using structural formula, write down the balanced equation for E, right? So the balanced equation for E, we can first trace our alkene from the alcohol thing, right? So what is the structural formula of our alkene? Because we want the balanced equation for the whole equation there. Right, so number one, we have to use Seitev's rule. So we want to use Seitev's rule to identify the major product that will be formed when this alcohol is going to undergo elimination reaction to form what this alkene. It's going to undergo dehydration. Right, so according to Seitev's rule, okay, by the way, what does Seitev's rule say? It says that if more than one elimination product is possible, the major product is formed when the H atom is removed from the C atom with the least H atoms are bonded to it. And of course, the secondary product is formed when the H atom is removed from the C atom with the most H atoms bonded to it. What do we mean? We are saying that obviously during the elimination reaction, it's guaranteed that this one is going to go because we want to remove water. So the hydroxyl group is going. But it must be accompanied with another H atom. So the adjacent H atoms are either this one or this one. These are one of them should go. So Seitze's rule is saying the H atom that must be removed is the one that is bonded to the C atom, which means we have two C atoms here, this one and this one, where the two H atoms are bonded. So which H atom will go? The H atom that must be removed is the one that is bonded to the C atom that has the least number of H atoms. So apparently the one that is the least is this one, this C atom here. So since it is the one with the least, the H atom is going to go. So once it's gone, it means this is what is going to be formed. So we have our C atom there. We have a double bond now here. That the H, now that the H atom, this H atom and the OH have gone, the OH group have gone. So we end up having this. This is what is going to be formed. And what is that compound? That's our alkene there that will be formed. So there it is. There it is. Okay, there is our alkene. There is our alkene. And what is the name of that? That's but2N. That's but2N. Right. And no one was actually asking its name. We want the equation, the equation for the reaction E, for the equation of E. The structural formula to the balanced equation of E. So we just have identified the structural formula of the alkene, the structural formula of our alkene compound Y. That's the major product that is going to be formed. Now it's reacting with what? With hydrogen. So we shall also indicate the structural formula of hydrogen, which is H. There we are, right? Then, if they react through hydrogenation in the presence of a catalyst, so our catalyst is either platinum. So in our case, already we have been told it's platinum. So it can either be platinum, palladium, or nickel. So we can't use this. We have already been told that platinum was used. So we have to also consider the one that has been already been laid for us. So what is then is the name of the product? Obviously, adding hydrogen onto the double bond is broken now. What is going to be added? 1, 2, 3, 4. The same number of C atoms are still there, right? And add the double bond when the double bond is broken. So there are our H atoms. There are our H atoms, right? So when the double bond breaks now, the two H atoms are now attached there. So this is our product that has been formed. And what is that? Apparently, this is butane that has been formed. So this is forming the structural formula of our equation. Now, the last question there is saying, write down the IUPAC name of compound Z. So apparently, we have just indicated the structural formula of compound Z. Now, we want its name. That's without doubt butane. So that's butane there because it's having how many C atoms? It's having 4 C atoms, right? So this is marking the end of the revision of this is the end of the revision.